now let's take a look at part B of problem 1. So again, we're given a network G, which is an acyclic and directed graph, and a source node S and sink node T, and we want to tell this time. So in the previous part, we devised an algorithm that would give us the best min cut of the graph. Now we want to say we want an algorithm that would tell us if this best min cut is the only best min cut of the graph. Is it unique or not? So this is a question. Now for easier notation, we'll define this here. We call edges of a cut the edges that's between them, like the edges which go from S to V except S. Okay. Now, I will first describe the algorithm, and then we'll take a look at the correctness proof. Just this solution, this pseudocode that I've written here, kinda is both the algorithm and the proof. We'll see. So this is the idea. Assume that there is another min cut, so it's not unique. Then these two cuts have to be different in at least one edge, right? So now the idea is, well, I first compute one min cut of the graph and consider all of its edges, assume it has k edges, and then at each iteration increase the capacity of exactly one of these edges and keep the rest of the capacities as before, and again compute a best min cut. Okay, now if you go, okay, so you will get a best min cut Si for the new graph, and you have S from before, and for every I from 1 to k, the number of edges that S has. Now, what we do here is that we check that whether this new best min cut has the same number of edges as the previous cut. And if so, we will be faced with a couple of cases, one of which would lead us to the fact that it's really not unique. But again, if you look at the other side, if it's if the min cut, best min cut of the graph is not unique, then well, there is another best min cut with one edge difference. So if you consider that one edge and find a new best min cut in the new graph, then if the capacities are the same, capacity of the new one and the previous one are the same, then that would mean that this edge is not in that one. And so the capacities are the same and the number of edges are the same, so that would mean that we have found a different best min cut. So it's not unique. Now, we will go in more details now. So, okay. So this is what we do. At each iteration, we increase capacity of exactly one of the edges of S by 1, and we compute the best min cut of the new graph, and we name it Si. Now, so have in mind that we have increased only one edge's capacity by 1. So what can happen to the mean cut value, mean capacity of the graph? The only thing that can happen is that it can be increased by 1. That's it. It cannot be increased more than that. So two cases can occur. If you consider this min cut Si, so either the capacity of S is equal to the capacity of Si in the new graph, or capacity of S plus 1 is the capacity of Si in the new graph. So either of these cases happen. Now, assume that, and again, have in mind, we only consider this whole thing if the number of edges in S and Si is the same. If it's not, then it's not going to be a best min cut for us, so we throw it away. And we move on to the next Si. We increase our I. Now, let's take a look at here. So assume that we are in the case where the capacity has remained the same, okay? Now, we will have two cases again. Either this edge that we increase its capacity is in the edges of the new cut or not, okay? So if it is not in there, then if you just consider SI, well, now this SI has the so capacity of SI here is now going to be in the original graph is going to be exactly as capacity of S. So we have indeed found a new best min cut, because here we assume that the number of edges of S and SI are equal. Also, with this condition here, we'll find out that, well, SI doesn't really contain this edge with the increased capacity, so its capacity in the new graph and the old graph is going to be equal. So SI is a min cut, and because its number of edges is equal to number of edges of S, then that would mean that it's a best min cut. And so S is not the only best min cut of the graph. Okay. Now the other case that might occur is that EI is part of this part of the edges of this SI, but we claim that this is not really possible, and here's why. So assume that it is part of the edges of SI. Now the thing is, if you consider SI in the original graph, its capacity would decrease by 1 exactly, because we increase the capacity of AI in the new graph. Okay, so then what will happen? That would mean that SI is a min cut in the original graph with capacity 1 less than the capacity of S. But this is in contradiction to the fact that S is a min cut of the original graph. So this is not a case that can happen. Now let's move on to the second case where the capacity of SI in the new graph is 1 more than the capacity of S in the original graph. Again, we consider two cases. Either EI is in S or it's not. Now, if EI is not in S, what does that mean? So that means that if we take SI to the original graph, its capacity is not really going to change, because we're using just edges which have been unchanged from the old graph to the new graph. So that would mean that capacity of SI in the original graph also is going to be 1 unit more than the capacity of S. And so this would mean SI is not at all a min cut in the original graph. And so in this case, we really have not found a min cut, rather a best min cut. The other case is if EI is part of SI. And now, again, if EI is part of SI, then if we take SI to the original graph, its capacity is going to decrease by exactly 1, because capacity of EI was increased by 1. And so SI is indeed a min cut in the original graph. And now, because we know that the number of edges is also the same, then here we can conclude that SI is a best min cut of the original graph. But what we need to check here is that SI is not equal to S. Because if it is, I mean, it is possible that we find S again, but if it is, then that doesn't mean that S is not unique. So we need to do this check here. And if they were not equal, then we'll return unique. We'll return not unique. And then have in mind that, so these are the only 2 points where you return something during your loop. And if you did not return anything during all the iterations of your loop, in the end you're going to have to return a true, which would say that, okay, if neither of these cases ever happen, then that means that the best min cut is indeed unique. Now, so here now we showed one side of it. We showed how to find another best min cut. But now let's prove the other side. So we want to say that if there exists another best min cut other than S in the graph, you're definitely going to cut it over here at some point. Okay? So let's say there is another best min cut, and well, there has to be at least one edge of one edge of S that is not in that other min cut. Okay? Let's say EI is the edge that the other best min cut does not have and S has. So we're claiming that in that case, that min cut is going to be found in this iteration. Okay? So in this case, you will be finding another best min cut in this increased graph. and you know that that best mean code exists, you know its capacity is equal capacity of S, and you know that it doesn't have EI. So if such a case exists, then it has to be found here, right? That best mean code, yeah, exactly. This case is where we catch another best mean code if it exists. So it has to show up somewhere here. And so this completes our proof. We proved that if there exists some other best mean code, we'll definitely see it here. And whatever that we find here, we showed that will be another best mean code or will not happen in these cases. So this is a proof of correctness of this algorithm. Again, as I said, this is not purely a pseudocode. I have written what cases can happen. Like, if you're really writing down the code, you don't need to consider this case because it's not gonna happen. And yeah, so if this loop, so at the end of the loop, out of the loop, you need to have a return true for the case where your best mean code is actually unique. And okay, now let's compute the runtime of the algorithm. So here on line 1, we have a computation of a best mean code, which in the previous part we showed will take poly of E and V. And so here, see, we have k iterations, and k is the number of edges of S, and that can be at most like n squared, which is again poly of V, the number of nodes. Now, at each of the iterations of our loop, so first you compute a best mean code. So you have a poly of V and E at each iteration. And these are just like comparisons here. So, well, let's say computing the capacity would take O of, E time, linear time in the number of edges. And again, this is just like a constant time checking. This case can happen. Again, this is a linear time computation of these capacities. And again, this is a constant time. And this check here would again at most take O of V time. So as you can see, during each iteration of the loop, we're spending at most poly of E and V time. And we're repeating this loop for at most n squared time. So eventually the whole runtime of our algorithm will be polynomial in E and V. So here's the proof of problem 2b.